Hello and welcome to my presentation. I'm going to be discussing CT airway segmentation using cascaded 2D UNet neural networks. There's a lot to unpack in that title, so without further ado, let's get started with the background information. Chronic obstructive pulmonary disease, or COPD, is an incurable inflammatory lung disease that results in obstructed airways and breathing difficulty. It is responsible for 9 million cases annually in the US and is the fourth leading cause of death as well. Currently, spirometry tests are used to diagnose and analyze the progression of COPD, but studies have shown that they can be inadequate in certain cases. For example, some smokers showing COPD symptoms have normal spirometry. Therefore, chest CT could potentially be used to more holistically diagnose and assess COPD severity. However, it is currently an impractical and time-consuming task, limited by the large number of airways that have to be manually assessed. In addition, different radiologists might produce different interpretations of the scan based on visual inspection, making it difficult to reproduce the results of manual analysis. This is where our project comes into play. Our goal is to automate the acquisition of airway diameter and wall thickening from chest CT using machine learning. To do this, we must first locate the airway system and segment it, which means finding its boundaries. The airway diameter and progressive wall thickening measurements can then be extracted from each segmented airway. What are the clinical applications of such measures? The airway diameter and wall thickening measurements could be used concurrently with spirometry to improve the accuracy of COPD diagnosis and analysis. Additionally, having an airway segmentation map could also be used for disease localization in the lungs or as a reference for bronchoscopy. How did we go about conducting the segmentation? We used a convolutional neural network, a CNN, a deep learning model created for image analysis. More specifically, we used a type of CNN called a UNet, often used for biomedical image segmentation. It takes in an input image and returns an output image. Moreover, a pre-trained liver segmentation model was used as the starting point of our UNet. This process is called transfer learning, as we are able to transfer the knowledge from an existing to a new algorithm rather than having to learn completely from scratch. At the bottom, we can see the architecture of a UNet, named for its U shape. At the top, we can see an example of a UNet taking in an input image and returning the desired segmentation, in this case of a cell cluster. A cascaded system of two sequential UNets were used. The first UNet roughly predicted the trachea's location and returned its coordinates. The second UNet could then zoom in on these coordinates to predict the trachea and its two branches. The dissimilarity coefficient was used to evaluate the performance of the network. Let us go over a visual representation of the cascaded system. We start with a CT slice and pass it into the first UNet, called the bounding box or BBNet, in order to get a bounding box around the airway. We can then zoom in on this bounding box and pass the zoomed data into the trachea bronchi segmentation or TBS net in order to get the final segmentation output. By using this cascaded system, we reduce the amount of area that has to be searched for the airway. To make an analogy, we're looking for a needle in a haystack, and focusing on the bounding box makes the haystack smaller, so to speak. We now have a general architecture for our algorithm and can now go about creating it. The process for creating a deep learning algorithm is divided into three main steps. The first is data curation and preprocessing, where the chest CT scans are collected and labeled. The data is formatted for input into the model and divided into independent training, validation, and testing sets. The next step is training, where the training set is inputted into the model, which can then learn to segment the airways. The validation dataset is used to evaluate the learning process and fine-tune the model. For those more familiar with machine learning, these are the parameters we use to train the model. The last step is testing, in which we evaluate the model's performance by making predictions on the aforementioned testing set. We will discuss these steps for both the UNets in our cascaded system. Let us start with the first model, the bounding box or BBNet. The data for the BBNet consisted of 100 chest CT series with a total of 40,819 slices. They were obtained with HIPAA compliance and the study was approved by an institutional review board. The data was labeled with ground truth annotations made by a board-certified radiologist. And out of the 100 chest CT series, 60 went into training the model, 20 went into the validation set, and the remaining 20 went into the testing set. The model was trained on 512 by 512 pixel CT images, downsampled to 224 by 224 pixels with field of view or FOV augmentation. Up or downsampling means changing the dimensions of an image without changing its contents. And field of view augmentation involves taking a central window 60 to 100% of the whole image area, translating it randomly in 4 directions by 50 pixels, and making the content in the window the final image. A visual representation may help with understanding. This is a visualization of a CT slice and its corresponding label made by a radiologist. FOV augmentation works by first taking a central window of the data and label and translating that window up, down, left, or right. In this case, the window was translated upwards. Lastly, the content in the window becomes the new data and label. Doing this changes the field of view of the airway in the image, hence the name field of view augmentation. Also note that the dimensions of the final data and label are 224 by 224, not 512 by 512, unlike the initial data and label. It has been downsampled. The dice coefficient of the trachea predicting model is 0.96. The dice coefficient is a number ranging from 0 to 1, and the higher the dice score, the more accurate the algorithm's predictions are. The 95% confidence interval is 0.71 to 1.0. Here we can see a violin plot of the dice scores. The ideal result would be to have the entire distribution above 0.8, but the majority of the distribution is above the threshold, so the model performed very well. We can see a correct prediction of a trachea. The location and boundaries of the trachea are predicted correctly. We can see a slightly less precise prediction of a trachea. The boundaries are predicted incorrectly, but because we are only using this model to return the coordinates of the trachea, the incorrect boundaries do not matter, only the location does, and the predicted location is correct. The only problematic case was when bowels in the abdominal region were predicted as airways, as the location was incorrect as well. However, this was not difficult to fix, as we could truncate the bottom, say, 50 slices of the scan where the abdomen was located. Doing this also allowed us to only focus on the lungs themselves, the region of interest. Consequently, the BBNet returned the correct coordinates of the trachea 100% of the time. We can now shift our focus to the second model in the series, the trachea bronchi segmentation or TBS net. The data for the TBS net consisted of the same 100 chest CT series used to create the BBNet. Once again, we had a 60-20-20 split between the training, validation, and testing sets. We could run a center of mass calculation on the predictions from the BBNet in order to obtain the coordinates of the trachea center. The TBS net dataset was then created by taking a sub-area centered on those coordinates, separating the main and branched airways into different channels, and upsampling to 224 by 224. Each slice in the training dataset had 3 zoom factors for increased quantity of training data, while the validation and testing datasets only had 1 zoom dimension. That was a lot of information, so let's go through it visually. At the moment, we're only focused on the trachea and its two branches, the mainstem bronchi, so we can discard any slices that are below half a trachea length below the trachea itself. Once again, using the needle in a haystack analogy, this allows us to minimize the size of the haystack, allowing us to find the needle more easily. We can then pass each slice in the scan through the BBNet in order to obtain the coordinates of the trachea center. We then take the median of the center x and y coordinates to prevent any outlier predictions from affecting the predicted airway location. We can then take a bounding box of arbitrary size about these coordinates, effectively zooming in on the airway. Lastly, the bounding boxes are all resized to 224 by 224 pixels for input into the model. Doing this makes the model more robust to airway size, which is necessary when we will be segmenting higher order airways. It might be beneficial to see an example of the data and labels passed into the TBS net. This is an example of a trachea in the trachea channel and the aggregate airway channel. The TBS net was also trained on the left and right mainstem bronchi, shown here. The left and right branches are separated into their own channels, and the whole airway is shown once again in the aggregate airway channel. The TBS net obtained a Dice coefficient of 0.94 with a 95% confidence interval of 0.51 to 1.0. The TBS net is conducting a more difficult task than the BBNet, so its performance is expected to be slightly worse. Here we can see a violin plot of the Dice scores for each channel. Once again, the majority of the distribution is above 0.8, so the model performed well. Now let us transition to the arguably more interesting task, prediction visualization. The TBS net learned the division between the trachea and the bronchi, anatomically referred to as the carina, with a high degree of accuracy. Displayed is the slice right before the carina. These are the radiologist-created labels showing the presence of a trachea, and these are the model's predictions. The model predicted the presence of a trachea correctly, as well as its location and boundaries. This is the slice right after the carina. These are the radiologist-created labels showing the presence of mainstem bronchi, and these are the model's predictions. Once again, it predicted the mainstem bronchi correctly, with the location and the boundaries also being predicted correctly as well. There were cases where the model was not so accurate, however. Close to the carina, the model occasionally output incorrect boundaries, as shown by the extremely unusual edges of the trachea prediction. The aggregate airway channel, however, was predicted correctly. In addition to the incorrect boundaries, the model also had trouble gauging where the right bronchus ended. The ground truth labels show the presence of the left and right bronchus, but the model only predicted the left bronchus. Model stopped prediction of the right bronchus too early. In conclusion, our cascaded system has segmented the trachea and the left-right mainstem bronchi with a reasonably high degree of precision. There were two issues. First, the algorithm had trouble identifying exactly where the trachea ended and the mainstem bronchus began. It is difficult to delineate the boundary between the two even manually, and there likely were some errors in the ground truth annotations for the data. For most cases, however, the model returned the division point within a few slices of the actual division, and this distance corresponds to only a few millimeters in real space. The second issue was that the algorithm ended predictions for the right bronchus too early. We hypothesized that the presence of 3 different zoom factors caused the airway size to fluctuate, and thus made it difficult to locate the ending point only based off of 2D cues. Now that the bronchi and trachea have been segmented, in what direction will future work go? The hyperparameters of our model were selected based on what values have worked well in the past, and a thorough search was not conducted. Such a hyperparameter search could be done to improve the performance of the model marginally. After the cascaded system has been fully developed, the recursive stage of segmentation can begin in order to segment higher order airways, deeper than the mainstem bronchi. After the segmentation is complete, we can use the dimensions of the scan to extract the desired measurements or train yet another model to use the segmentation map to output the desired measurements. Let's visually go over the recursive segmentation process. Using the predictions for a particular bronchus, we can find the center of the bronchus on each slice, and using these points, we can put a line of best fit through the airway. We can then take a subvolume centered around the line using the length of the bronchus, much like how we truncated the original CT slice using the trachea length. We can then rotate the subvolume so that the line is perpendicular to the plane of view and scale up its dimensions to equal that of the original CT dimensions. Finally, we reslice the subvolume and pass into the cascaded unit system once again. Note that the subvolume structure closely mirrors that of the original CT volume with a main airway and two branching airways. Therefore, the cascaded system will now segment the bronchi and its two branches. This process can be repeated for the other mainstem bronchus and for subsequent airways, allowing us to get a deeper look into a patient's airway topology and potentially scan for abnormalities in the airway system. And that concludes our presentation. I would like to thank Dr. Albert Shao for his machine learning and radiology expertise, Dr. Lewis Hahn for his data annotation and project guidance, Mr. Evan Masutani for technical guidance regarding the UNet, Mr. Kang Wang for providing his liver segmentation model, Mr. Brian Hurt for discussing the specifics of dice loss, fellow surfers Sulan Wu and Elizabeth Yam for sharing their knowledge, the members of Ada Lab for providing recommendations for how to better my algorithm and presentations, and finally, the SFP office for making this project possible. Thank you for your time, and I hope you have a great rest of your day.